Yes. So King Doc, thank you for preparing that. Um, all right, everybody, let's get started. A few good things to do today. I'll start off again. Updates on open source golf cart, open source ecology, refrigerator. Believe it or not, some updates on that, and stop on the 3D printer and new extruder designs for the 3D printer as well. So you see the hours graph on the right hand side. We're kind of like at this. Just to comment on that, we're kind of like at this low level around like a 10 or 9 or 8, 80, which means 80 to 100 developer hours per week. So that's, if you look at the equivalent of full-time people, that's like 2.5 or so. So that's where we're at right now. Definitely want to get this way up. And idea being that as we, well, moving forward on a book, so I am working on a book. Let me share my screen here. Those numbers that you see there, they will go up. How? Well, so OSC clubs, I will put more effort into that. That's a thing that's on a back burner. But regarding immediate absolute priority right now, so it's still about developing the extreme enterprise business model. Okay, so if you go to extreme enterprise, the theory there is the concept. Okay, extreme enterprise. It's a technical definition. So we can look at it technically, but the idea is with real open source development, the hope is still there, and not a lot of people are really showing this, but that the economics of such production are really robust and successful. And RepRap has demonstrated that a little bit, but there's still no clear visible precedence as far as how open source enterprise goes forward. And I was discussing this with a historian of open source named Katrina Mota, who is my partner and who wrote a thesis on the topic for her PhD. It's about basically about creating new opportunities and participation in technology. But one of the things we have with software compared to hardware, and we were actually discussing this, and it seems that one of the barriers is definitely very much cultural, because software started with open source. Like when people started maybe in the 70s with sharing software, all of that was open source. And then the idea of proprietary came about with the emergence of Microsoft. And after that, Linux rising from the ashes, I think after that, in the 90s. But in the 70s, everything was open source. The 80s, it went south. The 90s, it kind of started emerging again to the point that in 2018, 2019, open source software development is the norm. Why didn't it happen for hardware? One running theory here is that we'd like to propose is that you have 200 years of closedness. And I think it's fair to say that hardware started closed, right? So you had the Industrial Revolution. A lot of stuff there was proprietary. Patents started around that time, even though there were some early examples of open source like the steam engine with Trevithick's antidote to Watt's steam engine. Basically, after the patents ran out on the Watt design, we could see historically that the efficiency has jumped up to double. And that's because people were sharing in open new designs, and basically the technology was kind of unleashed. But by and large, everything else was proprietary. So we have that idea where people right now, I mean, when you talk to people, it's like nobody considers you sane if you talk about open hardware business models for hardware. Okay, so there comes the extreme enterprise. The promise still stands. So that's a prelude to Extreme Enterprise, and Extreme Enterprise says, okay, if companies can get extreme productivity by going centralized, going proprietary, we should theoretically be able to do better than that because we're eliminating competitive waste with collaborative development. So costs of development are shared. If designs are shared, basically like the same analogy as open source software, where right now, if you're going to do closed software for AI or computer vision or machine learning, you're crazy. Everyone goes to the open source pools that exist. So people like Facebook, Amazon, and Google, and all of them support open source. So the far opposite happens in hardware. Now, with the specific case of the 3D printer, I just want to bring this up just for reference for what I'd like to see with the 3D printer. So we know some numbers, and if you go through some numbers and studying Prusa printers, which is the most successful 3D printer company in the world, there's Lulzbot, who's very successful and growing very rapidly. But there are some numbers that we can look at. Lulzbot produces about 1 3D printer per person per day, 1/3 of a 3D printer per person per day, if you look at their productivity numbers. Prusa Research does about 1 3D printer per person per day. That means they've got a lot of employees. They make tons of printers. All of them do. But if you divide it by employee, the figures are 1/3 for Lulzbot and 1 for Prusa printers. I think we can do about 3 for OSE. But that does mean quality control. So going to the definition, distributed production, open source production engineering, meaning simple stuff that a lot of people can replicate. Distributed quality control, so that's a new word, but that's what I'd like to see. So I've got with the 3D printer that we do, which is getting to be tops. I think we can demonstrate that the productivity is super high. We can generate significant revenue and basically beat the efficiencies of other standard products. Now, Lulzbot is open source, and so is Prusa, but they are not decentralized. They're also centralized operations. They're not distributed. They've got a manufacturing facility and so forth. And here we're claiming, like, okay, taking it to the next level, saying, okay, now let's distribute the production, meaning we provide the blueprints of how anyone can get started doing this business. So that's a big point in progress, but that's what I see happening here. So specifically speaking, 12 printers produced in a single day. They could be shipped on a second day. Customer support can be provided on a third day. Okay, so 3 days per 12 printers. So 3 or 4 days. I'm counting 4 days. Give 1 extra day, but that means 3 printers per day production rate with high quality control, etc. So that's it. Does anyone have any questions about this? Does this make sense to anybody, or is this am I talking to myself, as I might be guilty of doing sometimes? Comments?
Do you mean in general on
Oops.
Recording is on.
Like, well, for one, we can start in general. Like, is it theoretically possible that small distributed operations are really high tech? Like, they actually have the quality control nailed out? Because a lot of times we have this one-off production kind of small enterprise stuff, you might be missing some of this quality control. And like companies go nuts about like going up to 6 Sigma or 3 Sigma. If you heard the term 6 Sigma, that means one product. This is in mass production. Like one product out of a million is bad. For us, I think the milestone would be like 2 or 3 Sigma. That means for one complex product like a 3D printer, we got one bad one that doesn't work. That'll be 2 Sigma, 1 in 100. I think we can even achieve like, yeah, I think 1 in 100 is definitely doable. Maybe even 1 in 1,000 once everything is really nailed out. Or if it's like so-called doesn't work, it's like readily fixed or it's just very, very minor. But getting to that level of quality control is the question. Is it theoretically possible to do that on a very small scale where there's not one Lulzbot, one Prusa, but many of them that are also at the very, very best level, meaning like peak top performance printers, not like a bunch of Chinese clones, which maybe not like really great. Maybe there's a lot of companies that go out of business or are simply not good. Is it possible to raise the bar for everybody? I definitely think it is. I think we could definitely do better. But what are the limits? What are the implications of that for the economy? Is it possible to do major change in the economy simply by the fact that we accept that, okay, we should develop openly so that everyone can have the best state of art?
I mean, my question is how would you distribute that quality control? I mean,
Yeah.
do you have some mechanisms in mind? I just have a hard time kind of conceptualizing that.
Is that Nathan?
Yeah.
Yeah. So it starts by first, okay, look at what distributed quality control is, or what quality control is in general. It's a bunch of procedures you have to follow in order to test your products. So if you go to, let's see, I think I have this on the wiki somewhere, but you can see the example of, let's see what happens for quality control on the wiki. But for example, Lulzbot publishes their quality control stuff. It starts with publishing what you're actually doing for quality control. Those are well-defined procedures. So the theory is, if you follow well-designed procedures, so that means, okay, you plug it in and you test your controller board with all the stepper motors plugged in, works. You test the controller, like you test it, do a bunch of tests. So tests can be explicitly done through the build process as you produce the kits. So for us, it would be, for example, producing the kits, like say 12 in a day. We have to add those quality procedures in there. That means the kit production is largely, okay, you might be cutting parts to size and doing cutting and preparing, but a lot of that procedure is simply quality control steps. So if you can define them, you can do them. When you do a defined quality control step, the product comes out as intended. Have the proper tests and design proper tests to say exactly, to make sure everything's going to work. And that's the thinking that has to happen. So in other words, like after we do the design, you do the production engineering, what's called the open source production engineering. You show one, how to make it, and two, what explicit steps you have to take to control the quality of the stuff that you're building. And so that you know that when you build it, guaranteed it's going to work, not a problem. And that's where we're trying to get to, or we're close to that. Like, like in the 3D printer builds that are real workshops, I can say, okay, you do this, you do that, and you do that, and your printer is guaranteed to work. These are, proven procedures.
Got it. So in distributed production, basically it would just be like in the form of documentation, the quality control checks. So
yeah, exactly. I mean, so you have checklists, and then there might be specific pieces of equipment. Like, for example, on the 3D printer, I've used like a small digital scale to see how strong the motors pull on the axes. You can make various tests with various diagnostics, and that's where like the open source diagnostic equipment and lab equipment becomes really sensible. Like if you're going to do R&D, you're going to have to get into R&D equipment, and organizations like Open Source Lab. There's another one, glia.org. I just found this out, and this is actually really awesome, glia.org. They're making medical equipment like stethoscopes, otoscopes, tourniquets for the Gaza Strip.
Awesome.
They're Palestinian dudes, but they also made the precious plastic filament extruder. I was so inspired by that. I posted it on Facebook, but the main OSE Facebook, they did the precious plastic extruder, and they're printing their medical devices of waste in the Gaza Strip as a resource-deprived environment. And wow, that is super exciting and inspirational. But take a look at that. Now, how did I get into that? Question was, I forget, got into this, the diagnostic equipment and R&D equipment and sensors and Arduino-based kind of stuff, which you can actually measure things with and document and look at your numbers, like just keeping records. Like I printed 100 part kits for the 3D printer, how many parts did I have to throw out? Like for example, you can look at Lulzbot's work, and they, for example, have all that work, and you'll see that okay, we made 1,000 parts. We had to throw out 32 of them because they didn't meet quality control specs and stuff like that. So all that process can be defined, and that's the point. It's a thing that, as long as you're aware that okay, there's defined procedures that you can engage in, then you can actually do them and get reliable products.
Got it.
Yeah.
So for the distributed model stuff you're talking about.
Okay. So let's keep going. I'll just report on a couple of other things, and that was extreme enterprise. It's a word that I might have used before, but now when I say extreme enterprise, I'm going to be very deliberate about what that means, and that is an enterprise that has better quality, price, therefore pricing, efficiency. So efficiency means productivity, and therefore price. It must include quality. But in theory, then you can use that as a model to bootstrap on developers. That's means that we're adding the refrigerator to our open source blueprint set because this is ridiculous. We can't have everybody go through this. If you're going to be super efficient, you get punished. You try to do something that's super efficient, and look at the numbers. There's 126 million households with one fridge. The power saved per year, if you were to do that, is 50 million megawatt hours of electricity per year in the United States alone. Dollars saved per year in America. Yeah?
Is there a reason that you're not using like the evaporative fridges instead? They don't require any energy.
Yeah, if we could get our hands on that, that would be good. That means evaporative, you probably have to have it integrated with the sun. That's more complex, so more integration. Yes, we'd love to do it. We don't have the design for that. Something that would be good. Have to be a system that really works. For us, this has been working honestly for the last 2 years, 1.5 years. Very low energy. So 8 watts. And then, do you have any particular ones that you think work, Jen? Would work for the CD go home?
I'm gonna look some up right now. I didn't know that you were working on fridges. It's just something that because of the whole prepper thing has come through my feeds on social media for years.
Yeah.
I'll look some up. I haven't had a need to use one, but I'll look some up for you.
Yeah, thank you. And look at the freezer to refrigerator conversion. Look up the Mount Best system. That's where we got this idea from. And Darkmo, he did this build and design. He documented all of that. It's on the wiki. There's actually a parts list for Amazon to do that. But yeah, it's like with $1.50 per year electricity cost.
Yeah, let's see. Yeah, first a note on the fridge. Sometime back, I put a link at the top of my slide there to the refrigerator discussion on the wiki about the compressor wear stuff. That was someone's back. I had ran across something just to note that there. There's some information about that. Although I think it sounds like you have a good idea of what the issues are with that. But I think I put a few different notes there about stuff. But so yeah, the other thing I'm trying to figure out on the CAD lately. Well, I guess first I got quite a bit of stuff done on the yeah. I mean on the golf cart. I guess that's another whole discussion. You think we're probably gonna skip a week, keep skipping a week on the golf cart thing, right? So
Yeah.
okay. Yeah. Anyway, I got some done on the bench and sort of the whole frame reinforcement with that. And also there's just more refinement to keep going there. And let's see, I added some stuff about possible FreeCAD tutorial things related to some of the sketch stuff that we talked about before and some of the design sprints. So that's all on my log. But yeah, on the D3D Mini, to keep going on that, I'm looking at kind of a lot of the printer stuff that I guess you were working on recently, and I guess the new Extruder update, which I think is just recent CAD updates. I've only got on that. And I see as you said before, I think you're designing it with some new parts and so on for that new, more professional version with the overhead design. So I'm trying to. I assume we want to keep the. On the one hand, I keep concerned with the unique part count, but obviously we're mostly talking about 3D printed parts. So I mean, having different versions of that kind of stuff, it's that's fine. Plus, we got to just experiment and see what works. I mean, you got to iterate, right? So I don't know. I mean, if I need to design some new, slightly different parts, 3D printed parts that are different from yours, because I know you said that for one thing, the motor mount wasn't working that great for the extruder. Wasn't holding that well, and your overhead design, I see you have a bunch of parts, but they're for the overhead. So, I'm trying to figure out what, I see you've got all the parts broken down in the, let's see, there's a D3D parts sort of library, and let's see, the one I've been looking at is one on GitHub plus the wiki updates that are recent. And so I've been going through all those files trying to look at those different parts. I think I saw a small duct fan, and then I saw versions with this really big duct fan. I guess it was created recently. Thinking that for the PVC to try to, keep it simpler and lighter, because I assume keeping the mass down on the extruder head would be better for the plastic version, so we don't need all the bulk stuff probably. But I'm going to try to piece together a bunch of those parts to have the updated extruder that will fit on the PVC Mini. So let's see. I guess if there's any thoughts, or I thought I saw, let's see, some updates to our printer roadmap a while back, but I guess I need to review that because I didn't think I saw a lot of changes. Are there any comments you can make about the direction you think that maybe some changes you're trying to do with the D3?
Yeah. So let's look at 3D printer roadmap. Oh, Abe, you actually read the wiki.
Yeah, I do read the wiki quite a bit.
3D printer roadmap, there should be one that's, no, what is this? Let me go to my recent wiki changes. That's good. I was working on thinking about some of the. Oh, this was, sorry, not roadmap. This was critical path. So there's a difference between a critical path and a roadmap. Roadmap is a general document. Critical path refers to more what you're actually setting as the priorities to that longer term roadmap. So that would be under, now that I remember, it would be 3D printer critical path. There's a subtle distinction. Forgot that wasn't under 3D printer roadmap, but 3D printer critical path. Okay, so let's take a look at this document. So the summary of it, without looking into details on it, the summary is, I think I mentioned these 3 items, which is scalability, modularity, and materials. And they all play into each other. So when you do scalability, such as the big 3D printer of 1 cubic meter, that's when we get into territory that not too many people have. But when you do such big printing, you need to start making your own filament, or otherwise your plastic is $20 $10 a pound, which is very expensive if you buy your ready-made spools. So you got to start making your plastic with the filament maker and so forth. And I showed the example of the Gaza Strip work, Glia.org, spitting out their own filament for real purposes. So that kind of stuff is real and amazing. And that also comes with getting into extruders, heater blocks that are bigger, like the Volcano and the Super Volcano. So I actually put, let's see, so the Super Volcano should be on this roadmap. So you see on the left-hand side, you got D3D V1902, which is the latest iteration, and you see the Volcano nozzle on top, which is what we're working with right now. Is before 1902, everything was smaller nozzles, just regular nozzles. I did discuss the self-paralleling axes last time, the new end stop, and now the distributed production engineering. That's called the extreme enterprise. So there's a little bit of more detail as far as how we can improve the production engineering. So for example, the 3D printed control panel. Right now we take a piece of plexiglass, drill a bunch of holes through it, and mount all our electrical components on it. Well, that control panel with all the holes in the right places can be 3D printed. So that's one of the small steps to improve production engineering. And then there's the open source rubber extruder. I put some brief notes on that, but that's the stuff. We're going to have to design an extruder for 3 millimeters that's optimized for rubber. And we are talking about, I won't explain this right now, but Shore 68 hardness. So look at Shore rating on the wiki, put some notes on that. But that means rubber that's soft, almost like the silicone rubber soft. That kind of stuff which cannot be printed otherwise. Like the Titan Arrow, I'm not sure it would print that with that kind of soft rubber. So we have to do one that's designed for it. The Titan Arrow, I mentioned last time, a few times ago, that it has this neck inside the extruder, where like a feed neck. We're going to remove that, make the distance between the drive cog and the actual hot element shorter. Okay. Now, another good thing there would be to do a two filament mixing extruder. Why? So, for example, we're going to have parts that have, like, for example, the universe that would have, say, PLA or ABS on the outside, and would have built-in bearings made of nylon or some low friction material like nylon. So you can print in 2 materials, or print shoes that have like soft rubber insoles and a harder outside or something. Let's print shoes. Okay. I'll step out just for a little bit once again. So we've got material. To be said. The rest is a lot of detail here, but the Super Volcano is one notable client that's in that 3D printer roadmap. So Super Volcano means, and how about going higher than a Super Volcano? like even bigger. So super volcanoes are 80 watts. Standard heater elements are 40 watts. What about 120 watts? Would that work even better for like 30% more throughput? We'll see. So there's heated enclosures, the big casting part, which I haven't touched, but I'm still very excited about, and that's a proof of concept needs to happen. We want to do universal access kits for sale. So with John's automated production engineering, universal access curriculum. There's low-hanging fruits like the small laser CNC mill, which we have right now. I mean, that needs to be productized. I mean, we've done it. Parts, including down to sub-millimeter precision. So MIG casting is sub-millimeter. Zinc aluminum alloys plus 3D printed molds for on-demand parts. Wire arc additive mining stuff like, for example, Dr. Metal injection molding, pellet 3D printing filament production. Did I say anything about that last time? Metal injection molding, the same stuff they use for metal injection. The plastic that has embedded metals, and then you can sinter that. That's getting into higher tech stuff, but okay. Higher temperature printing chamber. That's not really metal, but it's more high temperature, allows you to print in super high temperature stuff like PEEK or even PEI. PEI is thermoplastic. That's the stuff our small induction element in the nozzle, and then you dribble that to make a three-dimensional shape. So standard 3D printing with metal embedded film sintering, that's the kind of stuff that already exists. Plastic filament that's got embedded metal that when you then bake the 3D print, it turns into 100% metal. And that's good stuff. That's doable.
Yeah, I guess if that's printable on some of the smaller printers, that'd be more useful. Some of the metal stuff, obviously, I'm thinking probably isn't immediately relevant to the well, the plastic frame or the PVC frame or whatever we can do, it may not be as ideal for that. And I'm kind of, I guess part of the problem is with the plastic and PVC frame, we still don't know. I guess John will probably have some data for us pretty soon on how, how well we can reduce the flexibility of that frame and scale it and all that. So there's questions there. So I'm wondering for the immediate version on that, I'm thinking just trying to figure out what maybe the limits are of that. Obviously, to start with, it could be a very simple version, and it can always be upgraded with more, all the parts are interchangeable. You can upgrade to the super volcano and so on, more power and that kind of stuff, even for a small printer. But I guess at some point there's limits with the plastic frame probably, but
Right.
Well,
I would say that the idea, because even what you just said, the standard 3D printer. The Ecology turns out nice since we already have the CNC circuit mill, which with our 500-watt spindle can do aluminum. Okay, so we're good on that. We can start milling our new extruders, and I drew up in my notebook a very simple, I really want to knock it out of the park with a super simple high-performance extruder that does not cost $150. Or if you're talking about the super volcano with the Titan Arrow, you're talking close to $300 just for the extruder system. So that's insane. We got to do that for about $5. Yeah.
Yeah, so I guess the extruder options are probably I guess the main things we're looking at. I guess the Titan Arrow is what you're kind of standardizing, and maybe the Super Volcano, it sounds like Volcano, Super Volcano, whichever it is for now on most of the printers, right?
Volcano for now, because that can get you up to the 1.2 millimeter nozzles very reliably.
Mm-hmm.
That's 5 pounds per day printing rates.
Yeah, I think I've been listening to a lot of printer stuff to try to get up to date on some of that, and I heard that there's some open maybe consortium or something working on maybe a larger filament or diameter standard or nozzle standard, 5-6 millimeters, things like that. And I guess
it's stalled, but yeah.
Stalled. Oh, didn't.
I think it's stalled. I talked to the 3D guys. They told me about it, and then I talked to them at the East Coast Red Wrap Festival, and they told me that wasn't really happening or something like that. Yeah.
Yeah, maybe I don't know what the physics come out. Yeah, I don't know how the physics all work out on upping the size of the filament and plastic and all that. It probably changes the speed and melt temperatures and all that.
Yeah.
So let's see, I noticed you had that big fan duct design, which I assume is for the version you're working on. Do you think that kind of stuff is relevant for like the smaller printers, or you kind of want to standardize around some of those parts across the board?
Yeah, we need print cooling. And what I've done there with the integrated, so this picture here, with the integrated sensor holder / blower, I think it is a good idea.
Yeah.
We do want the sensors, like we're using the larger sensors because we want to do 1 meter printers and we want to do tiny printers. This is definitely going to work on a 1 meter printer where if you have an uneven bed, or like you can accommodate for more inaccuracy with a larger sensor, which allows you to have a larger sensing distance, meaning you can be safely away from the prints without hitting them. But yes, a cooling fan is required, so we got to do that somehow. And but once again, if we do like the V3 mini PVC, would this be relevant? Well, we need some kind of a print cooling fan, and this does it. So if we want to keep to this same sensor, this is a pretty effective way to do it. It's not, I mean, it's just a printed part, and it's pretty simple, so it doesn't cost us much outside of space.
I guess the system is pretty good.
To have really good print cooling, I mean,
Okay, so I guess the system is pretty good overall if you put more cooling. I see it's all kind of, they're all that way. They're all like aiming a lot of cooling at the part area, which technically is also the nozzle and the heat block. So I guess the system is pretty good at keeping its temperature what it needs to be and all that. So you can throw cooling at it and it's not going to, I guess, make the situation worse or anything with the heating. I guess it's.
Let me explain the cooling part. So the cooling part is when, okay, so the way that 3D printing works is you melt the new layer onto the existing layer. In other words, if you stole the print and you came back the next day, you can continue printing on it because the way it works is not by heat from the former layers, it works by the heat from the existing layer fusing into the layers below. Now, for the prints to be accurate, as soon as that happens, you want to cool the new filament that was deposited, otherwise it will wobble on you. So you can do like overhangs. If you have a cooling fan, the theoretical limit of a cooling fan is that you can print horizontally without support, because as soon as you extrude the plastic, it gets cooled and solidifies. So that's the kind of mindset
I noticed on the kind of the physics of it that the height or the amount of squish on the extrusion is really important, especially in the first layers. I kind of saw that's why you do the paper test and that kind of stuff I've seen. So squishing the extrusion on there is critical for bonding. Yeah, I'm surprised how much overhang you can do on a lot of these parts. So yeah, it's precision. So I guess that part, that big fan duct, I guess it could be printed with low infill, so it's probably not going to be that heavy. Then, have you printed tests of that yet, or you're just working on that, right? The CAD.
That's the print. That's my actual thing I'm using right now.
Oh, okay. You're using that recently. Okay.
Yeah.
Okay. So that.
Yeah, I'm using that. Well, actually, hold on a second. I'm not using that right now. The 1902 has the omnidirectional fan shroud from Lulzbot.
Okay.
And I said, okay, let's get rid of that, because first of all, you cannot fit it for the over-slung extruder with the volcano block, because there's just not the space in our current geometry. If you put the extruder on top, if you put the extruder below, you can use the Omni shroud, but the nozzle is way farther axis, meaning it wobbles more. So I'm expecting more accuracy using this system. What I'm showing on the screen, I'm expecting more accuracy because
Okay. Yeah, I was trying to decide how well that overslung design would work on other printers. And of course, I know in that version you're working on, you've got the two dual z-axis, but obviously on the Mini that's probably not pertinent. But the overslung design, I was trying to figure out if that was relevant for the PVC Mini, because now would be the time to change stuff to something like that. But I had set it up.
I'd say for you to decide that would be like see if the bed size that you can reach is acceptable. Because with the overslung, you can mount it in such a way that you gain yourself more space. Oh, sorry, did I cut out there?
No, I can hear you.
Okay. Yeah, so you got it. So if you use the overslung version, you allow yourself more motion area.
Yeah, I'm just looking at that. I think the issue on the PVC or plastic version here is the way. Yeah, it's kind of different. 'Cause the clamp I've designed, I guess, isn't really designed to attach up on the those corner pieces on the PVC corners. And I guess that's part of the issue, but yeah.
Still,
Well,
you're still good because you're mounting the clamps all mount to the frame. No.
yeah, they do, but the PVC corners or plastic corners are different from the pipe. The clamps are made to go on the 3/4 inch pipe, so the y-axes are a bit lower down than the top, whereas yours is right at the top of the metal frame. So yeah, you've got stuff to connect there. You have to do a different.
Yeah. Maybe then the suggestion is if you want to keep it simple. Yeah, the advantage to what you're doing right now is that it's more compact. Like here now we're getting top heavy, like all this structure at the very top of the printer. So maybe try to work out more motion area with your version.
Yeah, it's interesting. I mean, technically, if we're 3D printing the frame and stuff like that, it's good to think about all the possibilities because that clamp design, I mean, that seems like it's pretty close. So. But, I mean, technically, if we're 3D printing the frame, you can just about 3D print any kind of parts and make it connectable. So,
you can still make your clamp work if you go, like, right below the corner pieces. I think it'll still work.
If it was, if we enlarge the diameter of the clamp to go around the corner part, that could clamp on there probably, and yeah, depending on how you mount the y-axis on the clamp, then it would be at the top of the frame. So I think I'll look at that option.
Yeah. The other option is you make the corner pieces such that they go inside the tubes, not over.
Yeah.
So they same size as the sides, which would make it look a little bit more elegant too.
Yeah, because we're 3D printing the corners, well, they can be designed differently, too, technically. I mean, they're a closed part that way, but we could just technically design it totally different than the PVC style. So there's a lot of options there. As you go down the 3D printing route. It would be nice to try the over-the-top version just to keep everything more consistent.
No, the idea is the idea is we're not producing a 3D printer, we're producing a 3D printer construction set, and that's our value proposition. So it's scalability, modularity, construction set materials.
Yeah, because I guess it gives you more Well, it potentially gives more Z height too because it's up above, higher, and yeah, it just gives you more area. So if it's a better design.
Yeah, I mean, from a very practical perspective, if we're shipping this, it's a 12-inch frame, and a 12-inch frame fits inside a USPS flat rate shipping box.
Okay.
Which is 12 inches.
Yeah. So let's see. On that clamp, I think we talked about that. Did you print both versions of that clamp finally? Did that?
No, I'm sorry, I didn't.
Okay. Okay, not yet. Okay, because I think you said the 1 millimeter one, or was it? Yeah, I think you said the small gap one wasn't tight enough, right?
Yeah, it wasn't tight enough. It didn't appear
Okay.
tight enough, so I
Yeah.
did a 2 millimeter. Yeah. And
yeah, at some point, I guess John's the only other one that's actively working with the printers. At some point, hopefully this year, I wouldn't mind getting to working on an actual printer myself. So I'll have to get stuff set up for that. But it'll help get things moving a lot faster. I get a better idea of, how some of it works.
Do you have time to do that, or?
Actually build a printer. Yeah, I need to put in. I need to change some stuff. Put in a shelf. Just minor rearrange things here. I don't have a lot of space, but I like to have a printer in the corner next to the computer, and yeah, I guess I can just print PLA. It should be fine indoors.
Yeah.
And I guess we were working on enclosures and so on like that too. I don't know how relevant that is for the plastic frame because then there's thermal issues maybe as you heat up if the enclosure is maintaining, I don't know what temperatures they usually maintain for enclosures for high temperature stuff, but with a plastic frame, I figured the enclosure would actually have to be on the inside, right? But
it would be on the inside, and it's on the inside for the big one. The whole point of the frame is that you're avoiding contact with anything outside the bed. It's take a look at that detail again. You're absolutely avoiding contact with all electronics and metal outside of just like real minimal contact, so it would work with the PVC.
Okay, so yeah, I'll have to look at that again because I figured you were.
Very interesting because
you're.
Printer, I would see that can do high temperature.
Yeah, so I figured the outside would probably the enclosure parts mounted on that would be some kind of plastic panels or something like that.
Yeah, I was actually thinking PEI would be a good material actually.
Okay. Yeah, if it's insulating.
Goes up to 450 Celsius for its melting point.
Okay. Yeah, and then.
Is that?
Yeah, that gives us the temperature range. So yeah, I guess I'd have to figure out how. Well, I mean, with a printed plastic frame, we can figure out how to create mounts. I guess the clamp. Actually, one thing I know John was pointing out, I kind of left off the clamp was magnetic attachment points, which could be useful for that. I kind of forgot about magnets, and with the design of that clamp, that there isn't really a great place to put magnets other than. Well, it's so small. I made it so small there aren't areas that are great for putting magnet attachment points. But so maybe that has to be changed yet too. But yeah, I tried to minimize it so much that there aren't a lot of other usage options for it other than the axis mount. So I'm gonna have to think about that more too, though, because there's lots of other things we might want to mount with those clamps. I haven't gotten to a lot of that idea yet. Like, I don't. I guess you don't usually mount the you have spool holders mounted on your frames usually on the metal frames. That's probably kind of hard on the plastic if it adds more mass.
I have it inside it's in the vertical holes of the motor pieces of the Z-axis.
The spool holder?
So the motor pieces.
I'm thinking about the spool.
So the motor piece folds the rods for the axis itself. Well, think about extending those rods. The spool holder is more rods, but sticking out the other end.
Okay, so just longer rods coming out the top.
Yeah, but not a single rod, because that would be like too long. Just use another rod and stick it inside that hole. Because the rod for the axis itself would reach halfway into the motor piece, like you see in my CAD. It's actually halfway into the motor piece, leaving room for the spool holder rods to be inserted from the top.
Yeah. Yeah, that puts a lot of weight on one side, I think. On most of the printers, but
one side.
Both sides, two spools, or on your version you've got you've got the two Z-axis. I'm thinking of the plastic version that I've got so far is tends to be pretty lopsided, and I think it's going to have to have some feet down there to help balance it anyway. So it's like you need to design some printed clamp feet or something yet, but that's like another issue. There's still a lot of design curves because with it being top heavy, it's not just vibration. If we want to maximize the speed is an issue, but
you kind of want to bolt the PVC down to a table.
I mean, if you could put more weight towards the bottom, that wouldn't hurt. But let's see.
Yeah, there's really no weight there.
Yeah, I mean, if you could put spools, which sometimes having more than one spool of filament around your printer, well, that only really applies for active use because, as I understand, you really need to keep your filament sealed up because it goes bad, right? That's what I've been hearing. Unless you're using a dual filament system, then so and spools weigh a kilogram or more, right? So
you could potentially have smaller spools of stuff. For the PVC Mini, it is kind of 2 pounds is pretty heavy for a small printer like that. You can get away with smaller spools too.
Yeah, I guess there's different ways to mount it, or just print a separate spool mount system or something that's next to it, or hang it on the wall, or whatever. But a lot of options, but it may not be as easy to integrate the same. Yeah, I'm gonna have to go down a whole checklist of other things that have to mount on this thing, I guess. So. Or not mount. Yeah, I guess most of the direction options are related to the extruder, which is pretty easy to swap out, right? I mean, that's the main thing.
Yeah,
that's
modular.
All those components are already real modular, so.
So extruder, a lot of the work is focusing around the extruder because if you really want to nail thermoplastics So it was kind of interesting to see that. Okay, extruders. How do you build an extruder? If you start hanging out with extruders or like using them enough, to do.
Yeah, that kind of goes back to the distributive enterprise stuff you're talking about earlier, because a lot of these small printers, they get people interested and work it with stuff easy, but to do the distributed enterprise stuff that's interesting, it really needs to be scaled up to heavier stuff.
And fortunately, because automation and it can happen. So yeah, I think we're in pretty good times. Because miniaturization of technology means you can do all this stuff on a smaller scale. And imagine if you could do this mid-casting stuff, which is now, since a few weeks, a big question for them. Like, can you actually do that? Does that mean you have ready access to precision metal parts, like a VAT in 5 minutes for a print? We'll see. But definitely there's a lot of exciting things we can do on a small scale. But it has to meet industrial productivity on a small scale. That's the requirement. Otherwise, we're at risk.
Yeah, it seems like the precious plastic stuff, from what I kept hearing, was pretty good. I mean, it's a pretty big, his standard system is a pretty big machine. It's pretty heavy duty already, and they seem to have scaled that out. And they have a bunch of pods, as I understand, where they have recycling centers and they recycle stuff. They've managed to do that pretty well. I guess that's just in the Netherlands, but that it's going to have to be a different.
Yeah, I haven't, like, the stuff in the Gaza Strip